Okay, chapter 13, deserts. Let me get my little pen here. There we go, chapter 13. Deserts and wind action. This will be a little bit of a shorter one. Yeah, so let's jump to it. So, step one, what's a desert? Any arid region that receives less than 25 centimeters, which is about 9.8 inches of precipitation per year. So basically, if a place doesn't get enough rain or snow, then it's considered a desert. And here's one of the big fun facts for this whole chapter. A lot of people think that wind erosion will dominate a desert, and certainly it occurs, and wind is pushing things around. However, running water is still the predominant force shaping effect, cause of the shapes that we see in a desert, or at least the majority of the erosion and the majority of the things being moved around, sediment and that sort of thing. If you ever spend any time out in the desert, you will know that flash floods are a very serious thing, and you kind of have to be careful about where you sleep at night and where you drive to, and some of the places you hang out. But it's these flash floods that produce a lot of erosion and are the predominant shaping cause in deserts. So, where and how do they form? They can be found anywhere that the air is dry. What causes this dryness? Well, it's where air in our atmosphere is descending. That's one thing. And then two things, we can also get deserts where there's rain shadows. And I will jump into that in a second. So let's first look at descending air and what that's dealing with. So here we have the Earth, and the Earth spins, and while the Earth is spinning, there's also this cycle, this tendency of where wherever the sun is shining. So let's put the sun up here. Whee, the sun. Yay. And the sun shines down to the Earth, and where it heats up the air, that air wants to rise. And so what'll happen is it wants to rise, and it'll go to where it's colder and sink. And we should get a nice, happy sort of cycle like this, except the Earth spins. And due to this spinning, we get what's called the Coriolis effect. And it's let's erase some of that. And we get this Coriolis effect where we end up getting these sort of these cells at different latitudes along the Earth. And so what happens is we get these areas where we have sinking air along the 30-degree lines of latitude, and this sinking air is dry, and that's why we tend to find deserts along these latitudes. So if you kind of just look along this 30-degree north latitude, we find the majority of the deserts, and along the 30-degree south latitude, we find a lot of deserts. Another way we can get deserts is from rain shadow. So what happens here is we get warm, moist air that comes off the sea. It moves inland, hits a mountain chain, dumps all its rain, and then nothing really gets over to the other side. Or, sometimes things do, of course, but not enough, and we end up getting deserts on the backsides of these mountains. California is a perfect example of this. So, some characteristics of deserts: intermittent stream flow. There'll be streams that have almost nothing in them, if anything, as far as water is concerned. And when there are rainfall events, boom, they fill up and we get these flash flood events. And of course, there are some exceptions like the Nile River and the Colorado River in the western United States. Excuse me. We'll get internal drainage where the streams don't flow out of their basins, so they never actually make it to the ocean. The Great Salt Lake and the Basin and Range area in the western U.S. is a great example of this. Again, I mentioned flash floods. And we'll also get these washes and arroyos, which I'm not too concerned with. So, nice, lovely picture of a stream event. Point being here is these vehicles got caught in a flash flood along this stream. Doesn't look like much of a stream, right? However, when you get a heavy rain, say up on this mountain over here, that water can come running down this stream, and it's trickling right now, and then a couple minutes later it's gushing and the water, is up to this level. It can be very dangerous. I grew up on the outskirts of Austin, Texas, which was known as the flash flooding capital of the world. We had, I think, more deaths per capita every year due to flash floods than anywhere else in the country. Something like that. Don't quote me on that, but it's something like that. And every time we got like even half an inch of rain, there'd be water rescues happening all over the city, and it'd be on the news that night. Not that Austin's a desert, but it is an area where you can get these heavy rainfalls, and there's just heavy runoff. So, what about desert features here in the United States? Well, we've got a couple of different places here. We have the Colorado Plateau, and we also have the Basin and Range province. I'm quite familiar with the Colorado Plateau. I've hiked all over it. I've taught geology classes on it. But I'm a little less experienced with the Basin and Range province, and I kind of want to go visit, which, has a lot of that is over in Nevada. Anyway, so where's the Colorado Plateau? First off, the Colorado Plateau is this area. Let's just fast forward here. Is this area right here, and it's actually a place where the Earth's crust is quite thick. It's something like 40 to 60 miles thick. Which is fairly thick for the Earth's crust, the continental crust. And part of the reason we see the features we do there is due to that. But anyway, it's kind of circled around the Four Corners region, which is these four corners. It's about 1,500 meters above sea level. For comparison, here in northwest Arkansas, we're actually about 1,500 feet above sea level. So multiply where we're at times 3, and that's about the height or the elevation we get in the Colorado Plateau. The rocks there are similar to the rocks we find here in the Ozarks. They are quite flat and sedimentary, and they have all these plateaus and mesas and buttes. And something I didn't appreciate until I think after I got my degrees was that if you removed all the vegetation in northwest Arkansas, you'd actually see topography that looks a lot like this. We'd have all these mesas and buttes hanging around because the vegetation just isn't there to hold on to the eroding sediment to kind of keep it on the hillside without it washing off. So here's the reason the Sierra Nevadas are on here is I kind of mentioned that California has this sort of rain shadow effect, and it's due to these Sierra Nevadas here. The moisture from the coast just can't quite make it over there, and we get this big desert in this area. So again, we get these mesa features. So we get these mesas, we get these buttes, and we get canyons. So if you ever go to the Grand Canyon, this is kind of the stuff you see. This is this is in Monument Valley, and I mentioned way back when we looked at volcanoes that a lot of people probably think these things are volcanic necks, and they're not. They're sedimentary rocks. This rock layer right here, that formation, used to exist all the way across this area, and it's the same formation way back here on these buttes. So all those rocks used to be connected, and erosion has just brought things down over time. So we also have the Basin and Range province, and we haven't gotten to faults yet, but we'll talk about faults very soon. But it's due to the way that it faults, or the rocks fracture. Hopefully maybe you know what a fault is before we've even gotten this far, and earthquakes happen along faults. It's breaks in the ground where the rocks are kind of moving past each other. And we get these faults that happen in this Basin and Range province, and it's why it's kind of called this name. And I'll kind of show you this stuff here in a second, blown up. But it's characterized by these long, narrow canyons. You get these alluvial fans. If you remember what that is, it's these fans of sediment. It's kind of like a river delta, like you kind of have a delta of sediment at the end of a river. Well, we get these alluvial fans as sort of the streams that dump all their sediment as they come out of the mountains. And alluvial fans may overlap to form what's called a bajada. And then we also have this special sort of legs called playas, which are finest sediments travel to the center, and there's ponds, and they evaporate, and we get these playa things. So, how does this work? Well, we have a tensional stress here. So what's happening to the crust is it's being pulled this way and pulled that way, and we get these faults that form, and in the middle part of the crust here drops down. And as it drops down, then you get all this weathering and erosion on the sides of these valleys, and the sediment just dumps into the valley. And you get these big alluvial fans that develop. And then the thing fractures more, and you get more erosion, and the process sort of continues. And you get these sort of, you get the topography that we see here. Now, I want to give you a second just to look at this. This is what we're seeing here. You can see here. And just take a second. See if you can spot those alluvial fans. And they're all connected together now. Do you see them? Look, there's one sticking out here. But the whole other side of this canyon is just a whole bunch of series alluvial fans stuck together called bajadas. And then you also have this evaporite basin down here, and so this is salt. So whenever there is water, it will collect down here and then evaporates, and you end up with all these salt deposits. Let's look at this one. Can you spot the alluvial fans? There's one, and there's kind of another one here. And this one also kind of overlaps in front of that. So tons and tons of sediment that are just being eroded out of these canyon sides, these mountainous sides. And again, you can kind of see all the salt here in the bottom from the evaporites. So that's kind of deserts. But let's also talk about wind, because wind does have an effect in sediment transportation in deserts. However, the water is still doing most of the work. So, why do we get wind erosion in transportation? Well, one, you have huge daily temperature swings if you go stay in the desert. And I think I've said this before in class. People complain like, oh, if you don't like the weather somewhere, just wait 5 minutes and it'll change. It's changes so much. Here in Arkansas, the temperature swings we get day and night. I think right now as I'm recording this, I think it's 70 degrees outside. And tonight it'll probably get down to 55. And tomorrow, during the hottest point, it'll be 75. So there's like a 20-degree swing in temperature. Well, in deserts, which are usually found inland, you can find huge temperature swings of 60, 70 degrees, and these big temperature changes will cause a lot of wind, just as the air is moving around to those temperature changes. If there's enough fine-grained sediment, you can get dust storms. Just ask the people living in the Western Plains during the 1930s. Because something that happened was called the Dust Bowl. I actually find this time period very fascinating. It's when we were going through the Great Depression, and if you're a fan of history and how Americans survived through great adversity, this was one of the places and one of the times where people were put under a lot of stress. But basically what happened was the western part of the plains turned into a desert. Part of it was just bad farming techniques, so that farmers didn't really know any better. They were farming their land every single year. They weren't swapping crops around. Due to the depression, the price of grain was dropping. So basically, you farm. If you want to make as much money, you got to farm more. So they were farming more and more and more and more, and it ended up being this environmental catastrophe called the Dust Bowl. And if you ever meet a soil scientist today, that profession was basically started because of this dust bowl, where we really had to start paying attention to our farming techniques, and not only the health of the crop, but the health of the soil underneath it. Anyway, so you got these huge dust storms that happened in the 30s, and just there's a great Ken Burns documentary. If anybody's a documentary fan, you know who Ken Burns is, and he's done a lot of the great documentaries for PBS over the decades. And there's one on the Dust Bowl. Anyway, so these sediments from this dust can also be carried extremely far. There's Saharan desert dust, really fine grain sediment, and it gets carried all the way across the Atlantic Ocean. Ignore that. Ocean. Volcanic ash as well can be blown and carried quite far. So here we have Spain, and here's the coast of Africa, and you can see this huge plume of sediment that's just fine-grained sediments that's being blown off of the Saharan desert. And I think this also has a big part to play in how hurricanes will form, and these little sediment particles, I think, lend to that. But I'm not a meteorologist, and this is something I need to go look up and study more. But some of you feel free to go Googling and see if that's the case. And it makes me wonder. I know the Sahara Desert has, during the last few ice ages of the last couple million years, it's been a lot greener over here, and there's been trees, and it was not a desert. And I kind of wonder, were our hurricanes, were they less powerful because of this? I don't know. I gotta look it up. I'm not exactly sure. Anyway, probably just because the world was a little bit colder and you need warmth to warm up the oceans to get hurricanes. But anyway, this sediment can go all the way as far over to South America, and there are sediment deposits in South America, and you could find them and kind of trace them back to Africa. So there is wind erosion and transportation in the deserts, and they do make for some fun formations or fun features. I don't want to say formations. I only like saying formations. Geologic formation is like a bunch of rock beds. That's a formation. This is, I guess I would say, a feature. Anyway, it's called a ventifact. So whenever you see these rocks that have been sandblasted and have all these weird shapes, they're called ventifacts. And you can break down the meanings of that word. Venti, I believe, means window. And so you'll actually see these things get holes blasted through them. So it's like a window feature. So sand gets blown around. It's sandblasting. It can erode things. It's also just bouncing around. If you remember from when we studied sedimentation and also streams, that there's something called saltation, which is the sand grains bouncing along. So wind deposition, and this I think is important. This is really neat, and it's got something relevant to Arkansas. You can see there's a little thing right there, and I'll talk about that here in a second. But when we deposit wind-blown sediments, they're called lurs, or lus, or los. I have heard it pronounced many different ways. I call it lurs, just because the people taught me, which is kind of like, sounds like lurs, kind of like that. But not too much on the R, like lurs, lurs. Anyway. So it's a deposit of wind-blown sediments, primarily silt and clay, and it can have quite a bit of different mineralogy in there. But there's thick deposits here in the United States, and it is very easily eroded when you find it. I used to dig up a lot of fossils actually and find them in the lurs down here in Louisiana, back when I used to be a paleontologist for the state of Louisiana. And there were thick deposits down there. I mean, I remember I would stand underneath them, and I'd look up, and they'd be 20, 30 feet high. And they were relatively recent deposits. Where did they come from? Glad you asked. So, a lot of loess comes from the wind-blown sediment left over by the receding glaciers from the last ice age. So, if you remember when we went through glaciers, that there's this outwash down here and this glacial till, potato, potato, and it is unconsolidated and it's made of all sorts of stuff, all sorts of grain sizes. Well, if you get a heavy, heavy wind and blow it across this stuff, you can take it elsewhere, and once the wind calms down, you will deposit it elsewhere. So here, again, we can see a nice glacier back here, and we can see all this sediment, all this outwash, all this till that's resulted from this glacier. So, I've mentioned before how the glaciers, the continental glaciers, came as far south as St. Louis, Missouri, and as they were receding, they were dumping all of that glacial till out, and it was traveling down the ancestral Mississippi River, and I believe the Ohio River, I forget. Anyway, there used to be a river that went on this side of Crowleys Ridge, and then there's the Mississippi River on this side. And these rivers were gigantic. I mean, they had so much sediment in them. They were braided and not meandering like the modern Mississippi River is, but just tons and tons and tons of water and tons of sediment coming down there. And then you had all this wind blowing across the glaciers, or the leftover glacial till to the north, and a lot of that ended up being deposited in this area. And some of it is still there as Crowleys Ridge. Let's just erase this real quick because it's getting insane. So Crowleys Ridge is a leftover feature of the glaciers that once covered at least the northern part of the continent. So even though we likely didn't have glaciers here in Arkansas, although I can't help but wonder if some of these deeper valleys here on the northern side of the Ozarks, if maybe they could have snuck in a couple of really small ones. I wonder. At least some that stuck around for a year or three or something. I bet. Anyway, yeah, so we kind of have this glacial feature here. Even though a glacier wasn't right there, it's the leftover sediments. Now you know. Also, if I haven't introduced it before, we can break up Arkansas into these different sections, right? We've got the Ozark Mountains, we've got the Arkansas River Valley, and we've got the Ouachita Mountains, and then there's the coastal plain, and then the Delta, and then Crowleys Ridge is sometimes considered its kind of own geographic feature of Arkansas. Also, with wind deposition, we get sand dunes. So you can go to the beach, you can go to deserts, and where there's sand, we will find sand dunes. Yeah, and these sand dunes will actually create their own sedimentary structure. We've looked at them before. Do you remember what they are? And to go over how a sand dune works, the wind blows from one side and picks up the sediment, and it bounces along saltation, and when it gets to the other side, there's no more wind, and boop, it deposits. So these dunes will migrate over time as the sediment on the back end gets brought up and over and deposited on this end, and then more sediment, and you end up getting these little hash marks like this that we see. And what's kind of neat, and we'll talk about it later, is on Mars. This is my drawing of Mars. It's red. Very clearly it is Mars. On Mars, there is these sand dunes that migrate with the same process. So, migrating sand dunes, and again, we can kind of see this. If we take a cross section and look at them, we'll kind of see this feature, and this can end up getting preserved, and sometimes we find it being preserved in very, very, very massive deposits. And these would have been large sand dunes. Yeah, and this, I imagine if I drew a person here for scale, the person would probably be about that big. It's one thing this picture is lacking. It's very fancy looking, but there's no scale. Might even be smaller than that. Maybe like that big. Anyway. We also have these features here in Arkansas. I believe I took this picture at Lincoln Lake, which is just north of of Lincoln, Arkansas, which is basically a little bit west of Fayetteville. It's like a 20-minute drive west of Fayetteville. Although you can find crossbeds pretty much anywhere south of Weddington, or maybe even in some spots south of 412. As you get into the formations there that are a little more clastic, up around NWACC and anywhere north, we mostly find the Boone Formation, which is a limestone. So it's not clastic, it's not the sand grains. But you get down towards Fayetteville, you see a bunch of those hillsides, and those hillsides, every now and then you see a bluff on them. It'll be these large sandstone layers, and a lot of them you can find crossbeds in them. So you can see them here, right? So these would have been small sand dunes that were migrating in this area about 340-ish million years ago or so. I highly suggest, if you guys can get out to Lincoln Lake, there's a great trail that goes around it, and great geology. And if you can't do that, go down to Devil's Den, do the same thing. You'll see this stuff down there, and it's pretty fascinating, and it's neat. Do it sooner than later. As you go through this class, I mean, I remember when I took my general geology class, and there was this moment, and it's why I turned into a geologist, but there was this moment, I went outside, started hiking around and seeing this stuff, and I was like, oh man, I know what this is. It's so cool. Anyway, that's the end of the chapter. There should be a quiz over this on Canvas, and let me know if you've got any questions.